Okay, for what we have in looking at Torricelli's law, and we have for the set of problems, and we have from number 61. Here we have a spherical tank with a radius of 4 feet is full of gasoline when a circular bottom hole with a 1-inch radius is open. And we have posed the question, how long will be required for all the gasoline to drain from the tank? Okay, so we have in this problem, we have a spherical tank, and again the radius is going to be at 4 feet, and just setting up some things here. And okay, so you got the spherical tank, and we'll say we have just for what I have indicated in blue, okay, that is just going to be the gasoline that is being emptied from the spherical tank. And now just for some of the features that we have. Okay. All right, so we got for this tank. All right, so you have a 4-foot radius. And in the setup, okay, we can form a right triangle. I'll just add this other leg here. Okay, so say we have a right triangle. And we have, once again, in terms of the characteristics, okay, so we have the radius of the tank will be at 4 feet. And for what we have at the liquid level, okay, we have the radius r. And just some other details. Okay, so we got, let's say, at the liquid level, again, that is going to be at y. And if you notice, okay, so we have, in this particular case, I'm going to do just a little bit of an extension, okay, just to give you a little bit of visual insight. Okay, now I don't have everything set up in proportion, okay, but again, the distance from the center to any point on the edge of the circular layout, okay, is going to be at 4 feet. And with the liquid level, now it doesn't matter if you had the liquid level above or below the center of the circle, because what we have here, now I've got the liquid level at y, and you got 4 feet, so you got 4 feet from the bottom to the middle, okay, but from the middle, okay, to the liquid level, okay, liquid level is y, and for this little bit of difference, okay, we're having this particular triangular setup, okay, we're going to have at y minus 4. Now, if I had the liquid level to be below the center of the circle, okay, we would have 4 minus y. But again, the square of y minus 4 and that of 4 minus y will end up being the same. So in looking at what we have in the triangular setup, okay, so we have with, again, we have with the right triangle. So we have the radius of the liquid at r. And again, we have for the height of the triangle, we have y minus 4. But again, if I had 4 minus y, the Pythagorean equation would have the squares. Again, that of y minus 4 and 4 minus y would end up being the same. And again, we have a 4-foot radius. And setting things up, okay, now with the right triangle, okay, so you have the radius 4 is going to be the hypotenuse. And looking at expanding, okay, so you have r squared, squaring out the quantity of y minus 4, so we have y squared minus 8y plus 16 is equal to 16. Okay, and so we're going to have 16s to cancel out, and upon isolating y squared, or make that, then we have isolating r squared. So I can have this equal to 8y minus y squared, and we have utilizing the square root property of equality but keeping the positive half of this. Okay, since the radius is going to be a positive measure, okay, this is going to be the positive square root of 8y minus y squared. And again, for what we have at the bottom, we have a circular hole that is cut out, and for the area of the circular hole, so again we're looking at pi r squared. And again, we have for the radius, okay, that is going to be at 1 inch. Okay, but again, if we look at converting in terms of feet, 1 inch is going to be 1/12 of a foot. And squaring out, okay, so we have pi over 144 square feet. Now, in terms of establishing the cross-sectional area, so if we provide an overhead view, and I'm going to place two circles, one inside the other. The outside will be in reference to the overhead view of the tank, and the inside, okay, will be in reference to the liquid level. And of course you have the hole at the bottom. And working with what we have again for the overhead view, now we're looking at the cross-sectional area in terms of the liquid level. And again, we have the radius is going to be the square root of 8y minus y squared okay, so I have the square root of 8y minus y squared. And for the cross-sectional area, again we have a of y is going to be equal to also pi r squared, where we have a different radius. And we have upon squaring the radius, okay, so we have for the cross-sectional area, that is going to be equal to pi times the quantity of 8y minus y squared. And looking at what we have in the setup, so setting things up in accordance with Torricelli's law. So again, we have the cross-sectional area, a of y, dy over dt is equal to the product of the negative of the circular hole area. And we have times the square root of 2 times the gravitational constant times the liquid level variable y. So we have for the cross-sectional area, so we have pi times the quantity of 8y minus y squared dy over dt and we have negative a, so we have negative pi over 144. And we have times the square root of 2gy. So you have 2 times 32, and we have times y. Okay, and just doing a little bit of simplifying in advance. Okay, so we got pi's on opposite sides of the equation, so I can get those out. And 2 times 32 is 64, and the square root of 64 is 8, and 8 over 144 will be 1/18. So just doing a little bit of simplifying in advance. So we have 8y minus y squared dy over dt is equal to negative 1/18. That is from the square root of 64 over 144. And we have times the square root of y. Okay, here we can separate the variables, thus the differentials. So I can simultaneously divide by the square root of y and multiply by dt. And so looking at what we have also in the mix, I can just take care of the negative 1/18 if I multiply by negative 18. Okay, so if I go ahead and do this, so just raising the coefficients, okay, and then we'll separate the variables. So we have negative 144y plus 18y squared quantity okay, so I have dy over dt is equal to the square root of y. Okay, now dividing by the square root of y and multiplying by dt. So I'm going to have negative 144 y to the 1/2 plus 18y to the 3/2 quantity is equal to dt. And upon separating, we can now integrate. And for the antiderivative terms, okay, so we're going to have negative 96, that is 2/3 of negative 144, times y to the 3/2, and 2/5 of 18, we'll just leave this as a decimal, so we will say we have 7.2 times y to the 5/2 is equal to t plus c. And now, going back to the spherical tank, now we had it to be full of gasoline. And again, you had the radius to be at 4 feet. And so for what you have in terms of the initial amount, see, we have going from top to bottom. So you have y naught is equal to 8. Again, the initial condition, okay? And so carrying over to what we have in this equation. So we got y naught is equal to 8, okay? So plugging in 8 for y, okay? And what's going to happen here, okay, is that once you plug in 8 for y, okay, what's going to happen is that for the value of the constant, that's going to be right at negative 868.9. And by the time that the tank is empty, okay, so you have y of t is equal to 0, okay, And for what we would have here, okay, so with y at 0, we have 0 is equal to t minus 868.9, since we had the value of the constant to be negative. And looking at isolating t, we have, for the outcome, we have 868.9 seconds. And if I translate in terms of minutes and seconds, so this will be right at 14 minutes and 29 seconds. Okay, for the next problem, suppose that an initially full hemispherical water tank with a radius of 1 meter has its flat side as its bottom. And it says here that, okay, for the hemispherical water tank, okay, a bottom hole with a radius of 1 centimeter is cut out. And if this bottom hole is opened at 1 p.m., about when will the tank be empty? Okay, so for what we have in this setup, okay, so you have a hemispherical water tank, so you have like half a sphere. Okay, so we have the liquid level at y, and the radius again we have at 1 meter, and we have again the elevation or the water level is going to be at y, and we have the water level or the radius of the liquid at the water level y is going to be at r. And again, so you have again a hole that is cut out, and just for the area, so you got pi times the square of 1 centimeter, okay, since the radius is at 1 centimeter. But I'm going to rewrite this in terms of meters, okay, and again, so you're going to have, it takes 100 centimeters to make up 1 meter. But if I convert from centimeters to meters, I'm dividing by 100. So we have for the area in terms of square meters. Okay, so we have 0.0001 square meters. And again, just with the right triangular setup, okay, again, we have the radius of the hemispherical tank, okay, to be at 1 meter. And looking at what we have in the triangular setup, so with the right triangle, okay, so you have R, liquid level Y, and again, letting the hypotenuse reference the tank's radius, okay, of 1 meter. Okay, so we have with the Pythagorean equation, okay, so we have R squared plus Y squared is equal to 1, and isolating R squared, we have that equal to 1 minus Y squared, and with the square root property of equality but keeping the positive square root, we have the R is equal to 1 minus Y squared. And again, the initial liquid level is at 1, since we had the hemispherical tank to start out being full. And now, like what we had in the spherical tank earlier, once again we'll be looking at an overhead view. Okay, so establishing the cross-sectional area. Okay, so we have like an outside circle, and this being reference to the hemispherical tank. And putting in, once again, okay, for the liquid level, inside liquid, okay, so we have, again, with water. And again, you have at the base, okay, we have that 1 centimeter radius hole. And once again, for the liquid, okay, that's going to be defined whereupon the radius is the square root of 1 minus Y squared. And for the cross-sectional area, again, we have to be circular. So we have a of y is equal to pi times the square of the square root of 1 minus y squared. And so this will be pi times the quantity of 1 minus y squared. And so we have the tools at hand, and establishing what we have utilizing Torricelli's law. Okay, so you have the cross-sectional area of the liquid dy over dt. Again, we have is equal to the product of the negative of the area of the hole that is cut out at the base, and we have times the square root of 2 times the gravitational constant times the liquid level variable y. So looking at what we have here, so we've got the cross-sectional area. So we have pi times the quantity of 1 minus y squared, again dy over dt, and for what we have in the case of the cross-sectional area, again you have pi times the quantity of 1 minus y squared. Okay, and before I get too far ahead, okay, we have with the area of the hole. Okay, so you got 0.0001 square meters, and don't want to forget the pi. So you got negative 0.0001 pi. And we have times the square root. And we have 2. Now in the metric system, we're looking at 9.8 meters per square second. So we're using 9.8 instead of 32 since we're looking at metric units. And what I can do off the top, okay, we have pi on both sides. Then we have coming down, okay, to where we have 1 minus y squared quantity. Okay, have dy over dt is equal to the negative. And what I'll do here is, so you got the square root of 19.6. So you got the square root of 19.6, which would be 4 point something, and multiplied by negative 0.0001. Let's say that for that figure, just approximating. So you got like negative 0.0004427 among the first digits. And again, we have times, okay, the square root of y. And what we can do is go ahead and divide by this decimal, and so we have, and we'll say that rounding to about the nearest 2 decimal places. Okay, so you have 1 divided by this, so you have about negative 2258.77, and negative over a negative is going to be a positive, so you have plus 2258.77 y squared quantity. And we have dy over dt is equal to the square root of y, and separating the variables. So looking at dividing by the square root of y and multiplying by dt, so we have in the rewrite, we have minus 2258.77, and dividing by y to the 1/2, we end up at y to the negative 1/2. And we have plus 2258.77. Okay, y squared divided by the square root of y. Okay, that is going to be y to the 3/2. We have quantity dy is equal to dt. And integrating over both sides. Okay. So we have for the antiderivatives case, we're going to double first coefficient. So you have minus 4517.54. We say times the square root of y, or times y to the 1/2. And we have 2258.77. So if I take 2/5 of this and say round to the nearest 2 decimal places, so we have 903.51 times y to the 5/2, and we have is equal to t plus c. And again, we have with the initial liquid level, you have your y naught is equal to 1, since the hemispherical tank was initially full. So you have with y naught equal to 1. Okay, so if I have y at 1 and t is at 0, well, this will kind of distill to where we have the constant is equal to minus 3614.03. And then by the time that the tank is empty, okay, so y of t is equal to 0. So going back, liquid level is 0. We have is equal to t plus c. So we have c is, again, negative 3614.03. And for the time span, okay, so we have 3614 0.03 seconds. And in terms of time, okay, now we're looking at with 1 hour as being 3600 seconds. So you have like 1 hour and 14 seconds. Okay, so we have for the time, okay, so say like if you have, like say if you have like starting at 1 o'clock sharp, and it's like 1 hour and 14 seconds later, so that would be at 2 o'clock p.m. and 14 seconds. Okay, I don't know why the author had like asking for the exact time as opposed to just the amount of time. Okay, but it took 1 hour and 14 seconds. So if we look at starting at 1 o'clock sharp in terms of emptying the hemispherical tank, well, it should empty right at 2 o'clock and 14 seconds.